Okay, I've decided that it may make sense for me to make a few additional remarks on growth models. The first remark I'm going to make is about a notational difference. Up to now, I've been talking about the population at time t. I've been using notation k sub t. I think from now on, I'm going to attempt to differentiate between discrete time, so I'm going to use k sub t like this for discrete time, and I'm going to use the functional notation k of t for continuous time. Continuous time. And because we have this geometric model, this geometric growth model, and we have the exponential growth model, what I'll try to do is that I will try to write the discrete model kt equals k sub 0, 1 plus r to the t, and then I will use the continuous notation. I'll say k of t equals k of 0 e to the rt. So I will attempt to be consistent about that. So this is a notation. And let's see how long I can stay with that. So that's my first remark. My second remark is, now that there's yet another way that we can describe these growth models. Up to now, I've been talking about this geometric and this exponential. There is an equivalent way to express the exponential model. Let's rewrite this like this. K of t, using our new notation, equals k of 0 e to the rt. And in this case, I'm going to ask a question, and the question is, what happens to the change? How does k of t change over time? K of t is continuous function that tells us what the population is over time. So a natural question is, what is the change in k of t over time? That's d dt kt. Well, if we're going to do that, we should take the derivative of the right-hand side. So that's d dt k0 e to the rt. K0 is our starting population. It does not depend on t. So that should equal k0 d dt e to the rt. We know how to take the derivative of an exponential function. This derivative is going to be k0, that is going to be e to the rt times r. Let me rewrite that one more time. So the change in k of t d dt kt is going to be k. I'm going to write it one more slightly different way. I think I'm going to write it like this. R times k0 e to the rt. And now we look at this and we say k0 e to the rt. Where have we seen anything like that before? And we say, oh yeah, we saw that right there. So obviously we're going to do this substitution, and that means that this equals r times k of t. Let's rewrite that more nicely. I'm going to put a box around this, but we're going to rewrite this a little more nicely right here. And that is that the change in time of k of t equals r times k of t. Let's think about that for a second. What that says is that the change in the population at time t looks like the growth rate r times the population at time t. So we would call this thing a differential equation. This is a differential equation. And it is equivalent to our familiar exponential, to the exponential model. It's just written it in a slightly different way. And that would be kt equals k0 e to the rt. If you see either this, then this, you know that they refer to the same model. Let's rewrite this just one more time. And if d dt k of t equals r times k of t, then it must be the case that d dt k of t divided by k of t equals r. What this means is that d dt kt is the change in k of t, and we divide that by k of t. So this is the proportional change in k of t. This thing equals the growth rate r. There's one more thing that we should know, and that is that when we have the derivative of a function divided by the function, you may know this, this thing is equal to the derivative of the log of the function. So we have yet another way, another equivalent way to describe this exponential growth model. We can describe it as our k of t equals k0 e to the rt. We can describe it as by the differential equation d dt k of t equals r times k of t. We can describe it by this new proportional change, and that is the derivative of the log of k of t. So we have yet, let's see, I guess I can do it this way also. Proportional change, and then this is also the change in the log. All of these describe the same model, and now we can see that the growth rate r is the slope of the log of k of t over time compared to time. So that's why we say if we have the if we plotted against time, if we plotted the log of k of t, and we have some path, doesn't have to be constant. If we take the slope, this is k of t, this is the log of k of t. If we take the slope at any point, that slope is going to be the growth rate r. Let me make one last final general comment. Let's write our differential equation model one more time. We're going to say it this way: d dt k of t equals r times k of t. This is our familiar growth rate, exponential growth rate model. There is something which is very, very, very closely related to this. Let me write it one more time. And that is going to be this model, which is the change in the population k of t over time equals r times k of t. This so far looks very similar, but we're going to multiply it by something. And what we're going to multiply it by is 1 minus k of t divided by a special number. That's going to be k, big K, and I'm not going to put any subscript on it. I'm going to multiply this, and this thing is called the logistic growth model. The logistic growth model was, I think, first proposed by a Belgian mathematician named Verhulst. Verhulst. And I think 1820, maybe 1828 or so. So this K here is called the asymptotic carrying capacity. If you were to plot this thing over time, T, the population looks like this. It grows for a while, and then it hits some asymptote at the level big K right there. And so we have not unbounded exponential growth, we have bounded growth. You can see that when K of T is much less than K, like down here, down in here it's much less than K, then K of T divided by K is small, so 1 minus K of T over K is close to 1. This thing is small, so this whole thing is close to 1. So when I multiply our R K of T by 1 minus KT over K, this thing is almost 1, and it looks almost like it's exponential. When K of T is close to K, then K of T over K is close to 1, and then this term is going to be close to 0. When K of T, so the change in K of T is going to be close to no change. It's close to 0. When K of T equals exactly K, then this multiplicative term is going to be 0. And there's going to be no change in K of T, and K of T is going to be constant. Let's see. Let me say one last thing. When K of T is greater than K, if K of T is bigger than K, then K of T, then 1 minus K of T over K is going to be negative. And that means that the change in K of T over time is going to be negative. And so that means that the population declines. So if we're up here, then over time, it's going to decline back down to K. It turns out that this differential equation model and this logistic growth model that we've now just introduced are used quite a bit in epidemiology and biostat. So there's a long history that intertwines demography with epidemiology. And so I thought it would be important to introduce this differential equation way of doing things. We may talk a little bit about epidemiological models towards the end of this mini class. So I thought I would introduce it now.